Alright, hello to all my friends from Math 250B. I decided to make a little video because we're having an exam on Monday and I'm not going to necessarily have a lot of time to meet other than the review sessions this weekend. So the first problem on the quiz gave a lot of people some trouble, and I thought it might be worth just showing you the solution rather than just having you read it. So I've put the matrix on the board here. It's a 3x3 matrix, and you remember that the question was asking you if this matrix is diagonalizable or not. In other words, is it non-defective or is it defective? And the thing we have to do is test each eigenvalue to see if each eigenvalue pulls its weight. Okay, and so the first step in solving this problem is to find the eigenvalues, and that's where a lot of people had trouble. So let me just remind you that what you have to do is take the determinant of a minus lambda I. Okay, and so what that would mean is that you're subtracting lambda from the main diagonal entries. Okay, so you subtract lambda like this, and we'll get something like that. By the way, a few people on the quiz took the original matrix and started doing EROs to it, and you cannot do that because what you really want to do is take the determinant of the original matrix A minus lambda I. Okay, so it's going to have this form. I've subtracted lambda from the main diagonal entries. Now what you have to do is evaluate this 3x3 determinant. That, in some cases, can be very challenging. So what you want to do is look for an easy way to evaluate the determinant. And that doesn't necessarily mean that you'd necessarily want to just choose the first row or column if you're cofactor expanding. In fact, it's the middle column that everybody should have noticed has a lot of zeros in it. Okay? You can use the first row or the first column, but you're going to have a much messier expression for the cofactor expansion because you have more numbers to deal with here. Okay, so if you need to, go back and review determinants a little bit, because if you can't get these eigenvalues right, it's very hard to really do the rest of the problem. And so I wanted to go over that with you. Okay, so the middle column is a good column to choose, and remember the pattern, plus, minus, plus. So this is a plus entry, and I'm going to take negative lambda, which is the entry in the 2, 2 position. I'm going to cross out that row and column and multiply by the subdeterminant obtained by using the 4 corners. Okay, so that's going to be negative 1 minus lambda times negative 1 minus lambda. Okay, so I'm squaring that. And then minus 1. Okay? Now, you do not necessarily want to multiply this all out, okay, because that would give you a third degree or cubic polynomial, and those are harder to factor. You really want to get this thing in factored form. So you've already got minus lambda factored out, and so that's perfectly good. Inside of these brackets here on the right, we can actually expand it and get a quadratic. So you see you have lambda squared, right? And then you're going to have plus 2 lambda, and then plus 1, and then minus 1 from right here. Okay? And the plus 1 and the minus 1 cancel. Here you have a factor of lambda in both of these two terms, so I can actually pull that out. I have minus lambda, I have lambda, and I have lambda plus 2. Okay? And our whole objective right now is to set that equal to 0 and solve it for lambda. Okay? So be a little bit careful that you are putting down the right value for lambda. When lambda plus 2 is 0, that actually means that lambda is negative 2. So there's a sign change here. Okay, and of course these two lambdas correspond to 0. So you're going to get 0 and minus 2. All right? Now the question is, do those eigenvalues pull their weight? All right? So obviously negative 2 only came out one time as a root of this equation, so it will definitely pull its weight. The other eigenvalue came up twice, so it might pull its weight. There's a lot of people who are still assuming that if I have a repeated eigenvalue, that the matrix can't be diagonalizable. But it might be, right? It might be. We have to investigate further with any eigenvalue that got repeated. So let's take lambda equals 0. And let's see if it pulls its weight, which is 2. So it would have to give us 2 linearly independent eigenvectors. Let's check it out. I'm going to take the null space of A minus lambda I. Well, lambda is 0, so I don't have to subtract anything. I'm just taking the null space of A, and here's what A is. Okay, this matrix has to be not invertible, and you can clearly see that it's not. All these rows are actually just multiples of the first row. Okay, and in fact, there are 2 free variables. I can see that already, right? There's 2 free variables here, which means that the eigenspace corresponding to 0 will be 2-dimensional. I will get that lambda equals 0 pulls its weight. So at this moment, I already know that the matrix is diagonalizable. Now, I'm not done with the question, because the question is asking me to find the eigenvectors and to build the matrix S and D that we talked about in class. So let me show you what you want to do here. This is just an old problem, right, that we learned much earlier in the semester. You have sort of 3 variables here, x, y, and z, right? And this equation just says that negative x plus z is 0. And x is the leading variable, so z is free. I'll call that one t. And then x, if you just solve this equation, x has to be the same as z, so I'll say that that equals t as well. Now, y doesn't show up, right, because it's got scalars of 0 in front of it. That doesn't mean that y itself is 0, though, right? The fact that y doesn't appear in this equation just means that it's free, okay? So I'll call that r, and that's also a free variable. Okay? So my null space is basically all vectors of that type, t, r, t. And if I bust out the variables, much like we did earlier in the semester, I can find a basis for the null space. Okay, when I bust out the t, I get 1, 0, and 1. And when I bust out the r, I get 0, and 1, and 0. Okay? Now the other eigenvalue is negative 2. So for this one, what I have to do is I have to look at the null space of what I get when I subtract negative 2 from the main diagonal. Well, that just means I'm adding 2 to the main diagonal. So if I add 2 to the main diagonal, this is the matrix that I'm going to get. All right? And of course, the bottom row is the same as the top row, so I'll just cross that one off. And now, when I'm doing this null space calculation, it is okay to do EROs. All right? So I'm going to multiply the first row by negative 3 and add it to the second row. So it's going to be something like that, if I did it right. Okay? And then I can divide this through by 2 if I want. So I'm going to get 1, 0, 1 on the first row, 0, 1, negative 3 on the second row. Okay? So again, z is a free variable. See, let me circle my pivots. You should always be circling these pivots, right? Z is free, so then y is just 3 times z, because you see, this equation says that y minus 3z equals 0. So y has to equal 3t, and then from the top line, x plus z has to cancel to 0, so I get negative t. All right, and so when I bust out the t, I'm going to get my basis here. It's a little bit skinny, but I can fit it in here. Negative 1, 3, and 1. Okay, so look what happened. We got lambda of 0, 0, and negative 2. The 0 eigenvalue gave us 2 vectors, and the negative 2 eigenvalue gave us 1 vector. So the way we finish off the problem then is we just simply have to write down the matrix S and the matrix D. So let me show you that real quick, and then we'll be done. So what you do, if you remember the procedure here, is, and this is just writing it down, the matrix S is built by putting the eigenvectors into the columns of the matrix. And it actually does not matter what order you put these 3 vectors into the columns. I'll just put them in the order that we see them, but be aware that you can change that if you want to. So there's S, and then the D is just the diagonal matrix, where the lambdas are going down the diagonal in the same order that you chose the eigenvectors. So we put the eigenvectors corresponding to 0 in the first two columns, and then the eigenvector corresponding to -2 went into the last column. So the way this would look would be basically like that. Okay, I can put all these zeros in here too if I want. Okay? And remember that basically the key equation then is that S inverse times A times S is equal to D. Notice that S has to be invertible. If you have a matrix S that has like a column of zeros in it or something, or a row of zeros in it, it can't be right, because S must be invertible. D, of course, does not have to be. And let's see, what else did I want to say here? I guess that's basically it. Oh, one more thing. I never asked you on the quiz to actually find S inverse. And I probably would not do that on the third midterm that you're going to take, because that, at least for a 3x3, that involves some much older material where we were finding inverses of 3x3 matrices. That's kind of a longer process. You'd either have to use the Gauss-Jordan method, or you'd have to use the adjoint method, if you remember that from several weeks back. I'm not going to be interested in that for this exam. Maybe for a 2x2 I would ask you to do it. But anyway, you don't actually have to find S inverse. You just have to find S and D and know this relationship. Okay, so I hope that this has been helpful. You really have to be very careful in getting the eigenvalues. Okay, please practice that determinant calculation. The determinant of A minus lambda I, right? You generally, with a 3x3, you generally don't want to be using the arrow method at this point, because you're going to get 6 terms, and generally they're hard to combine together. It's better to look for a row or a column of zeros and see if you can exploit that. Okay? So if you have any questions, feel free to talk to me, send me email, or come to my review sessions, and I will do everything I can to help you guys to get fully ready for the midterm coming up on Monday. Thank you.